Does each table represent a linear or exponential function? Explain. Part A. As x increases by 2, y also increases by 2. So the rate of change is constant, and the function is linear. Part B. As x increases by 1, y is multiplied by 3, so the function is exponential. Evaluate each function for the given value of x. Part A. Y equals negative 3 times 4 to the power of x. X equals 2. Begin by writing the function, then substitute 2 for x. 4 squared is 16, and negative 3 times 16 is negative 48. So when x equals 2, y equals negative 48. Part B. Y equals 2 times 25 hundredths to the power of x. X equals negative 3. Begin by writing the original equation, then substitute negative 3 for x. 25 hundredths to the negative third power is 64, and 2 times 64 is 128. So when x equals negative 3, y equals 128. Graph f of x equals 5 times 2 to the power of x. Compare the graph to the graph of the parent function. Describe the domain and range of f. Begin by making a table of values. Substituting negative 3 for x in f of x, you find when x equals negative 3, f of x equals 5/8. Similarly, when x equals negative 2, f of x equals 5/4. When x equals negative 1, f of x equals 5/2, and when x equals 0, f of x equals 5. So to graph the function, you want to plot the ordered pairs negative 3 5/8, negative 2 5/4, negative 1 5/2, and 0 5. Then draw a smooth curve through the points. The parent function is g of x equals 2 to the power of x. The graph of f is a vertical stretch by a factor of 5 of the graph of g. The y-intercept of the graph of f, 5, is above the y-intercept of the graph of g, 1. Now you want to find the domain and range. The domain is the set of all possible x values. From the graph, you can see that the domain is the set of all real numbers. The range is the set of all possible f values. From the graph, you can see that the range is the set of all real numbers greater than or equal to 0, which can be represented by the inequality y is greater than 0. Graph f of x equals negative 25 hundredths to the power of x. Compare the graph to the graph of the parent function. Describe the domain and range of f. Begin by making a table of values. Substituting negative 2 for x in f of x, you find when x equals negative 2, f of x equals negative 16. Similarly, when x equals negative 1, f of x equals negative 4. When x equals 0, f of x equals negative 1. When x equals 1, f of x equals negative 1/4. And when x equals 2, f of x equals negative 1/16. So to graph the function, you want to plot the ordered pairs negative 2, negative 16, negative 1, negative 4, 0, negative 1, 1, negative 1/4, and 2, negative 1/16. Then draw a smooth curve through the points. The parent function is g of x equals 25 hundredths to the power of x. The graph of f is a reflection in the x-axis of the graph of g. The y-intercept of the graph of f, negative 1, is below the y-intercept of the graph of g, 1. Now you want to find the domain and range. The domain is the set of all possible x values. From the graph, you can see that the domain is the set of all real numbers. The range is the set of all possible f values. From the graph, you can see that the range is the set of all real numbers less than 0, which can be represented by the inequality y less than 0. Graph y equals 3 times 2 to the power of the quantity x minus 1 minus 3. Describe the domain and range. Begin by graphing y equals 3 times 2 to the power of x. Notice that the equation y equals 3 times 2 to the power of the quantity x minus 1 minus 3 is of the form y equals a times b to the power of the quantity x minus h plus k. Rewrite the equation to identify h and k. Here h is 1 and k is negative 3. Because h is 1, you want to translate the graph y equals 3 times 2 to the power of x 1 unit right. And because k is negative 3, you also want to translate the graph of y equals 3 times 2 to the power of x 3 units down. So the point 0, 3 maps to the point 1, 0, and the point 1, 6 maps to the point 2, 3. Notice that the graph approaches the line y equals negative 3 but does not intersect it. Now you want to find the domain and range. The domain is the set of all possible x values. From the graph, you can see that the domain is the set of all real numbers. The range is the set of all possible y values. From the graph, you can see that the range is the set of all real numbers greater than negative 3, which can be represented by the inequality y is greater than negative 3. An exponential function g models a relationship in which the dependent variable is multiplied by 2 5/10 for every 1 unit the independent variable x increases. Graph g when g of 0 equals 4. Compare g and the function f of x equals 4 times 2 to the power of x over the interval x equals 0 to x equals 2. Begin by making a table of values. You know when x equals 0, g of x equals 4. To find points to the right of 0, 4, multiply g of x by 2 5/10 for every 1 unit increase in x. 4 times 2 5/10 is 10, and 10 times 2 5/10 is 25. To find points to the left of 0, 4, divide g of x by 2 5/10 for every 1 unit decrease in x. 4 divided by 2 5/10 is approximately 1 6/10, and 1 6/10 divided by 2 5/10 is approximately 6/10. So to graph g, you want to plot the ordered pairs -2 6/10, -1 1 6/10, 0 4, 1 10, and 2 25. Then draw a smooth curve through the points. Now you want to compare the graph of g to the graph of the function f of x equals 4 times 2 to the power of x over the interval x equals 0 to x equals 2. Both functions have the same value when x equals 0, but the value of g is greater than the value of f over the rest of the interval. The graph represents a bacterial population Y after X days. Part A. Write an exponential function that represents the population. Begin by using the graph to make a table of values. You can see from the graph that when x equals 0, y equals 3, when x equals 1, y equals 9, when x equals 2, y equals 27, when x equals 3, y equals 81, and when x equals 4, y equals 243. As x increases by 1, y increases by a factor of 3. And because y equals 3 when x equals 0, the y-intercept is 3. Substituting 3 for a and 3 for b in y equals a times b to the power of x, you find that the population can be modeled by y equals 3 times 3 to the power of x. Part B. Find the population after 12 hours and after 6 days. Because 12 hours equals 1/2 day, to find the population after 12 hours, substitute 1/2 for x in the equation y equals 3 times 3 to the power of x. 3 times 3 to the power of 1/2 is approximately equal to 5 19/100. To find the population after 6 days, substitute 6 for x in the equation y equals 3 times 3 to the power of x. 3 to the 6th power is 729, and 3 times 729 is 2,187. So there are about 5 bacteria after 12 hours and 2,187 bacteria after 6 days.